How does the second level behave when I introduce a sudden change into the first flow? Now we know, and I would like you to develop this ability to be able to do this without doing the math, right? I want you to be able to sketch it out and work it out in your mind. So we've covered this in great detail, the first order system, and I hope by now you have strong intuitions about what that graph is going to look like. You know that the level there is going to do something like this, right? And then that means that if f1 is like a k times that, it's also going to do, it's going to look exactly. So if that is what f in looks like, I can actually ask the question, what happened, or what would have happened if instead of this input, what f1 looks like now, right? So the response of these two systems in series, I can basically say it's the same as I would imagine the first system would respond, but just with a different input. And so a way of thinking about this, and we've talked about this convolution, is that initially, we can see initially that h grows really, really rapidly, and it then eventually levels off. And we can see that there's a discontinuity in the derivative of the output signal, which corresponds to the discontinuity in the value of the input signal. And this is a kind of a general rule for first order systems. For first order systems, I integrate to obtain the output, but I integrate only once. And so derivatives, the original system input, if that has a discontinuity, that translates to a discontinuity in the derivative of the output. Okay, so it's another way of saying this is that first order responses have a sharp corner at time 0 if we look at the step response. Now what about the response of this tank now? This tank does not have a discontinuous input. It has a continuous input. Does that make sense? And so when I put that continuous input into this integration system, I expect a smooth derivative. In other words, a derivative that does not have a discontinuity. Okay? What does that look like? It looks like a sigmoid. In other words, S-shaped curve. That's what a sigmoid means. But what is important is at time 0, if I zoom in on that, it's smooth, right? Where if I zoomed in on this, it was sharp. Now smooth and sharp are words that we use where mathematicians would say discontinuous first derivative and continuous first derivative. Right? So when we say something is sharp or has a corner or something like that, that means if I were to take the derivative of that, I would see a discontinuity in that derivative. If I say it's like nice and round or smooth, I expect to take the derivative and end up with a continuous derivative. So this is what's happening, right? So we can predict that the second order response will have the sigmoidal shape, the smooth shape that doesn't have a discontinuity in the derivative. This response for two first order systems in series with the same time constant is what effectively results when I have a damping coefficient of 1. So the damping coefficient is just in this standard form of the second order response, and we can see that the response is exactly as I drew it. So you can see that we have this blue line is the step response, and we can see that the initial value, at that initial value, we go smoothly from 0 into this curve instead of having that sharp corner. The signs that this is not a first order step response is the fact that it has non-zero higher order derivatives. Okay? First order systems have step responses which have discontinuous, because there's only one differential equation. And so think about it. the left-hand side of that derivative, or the left-hand side of this equation, is the derivative of the function, right? So for first order systems, if there's any discontinuity in the right-hand side, it is just there. It remains there in the right-hand side, and so the derivative of h, there it's very clear in this equation, the derivative of h is simply given by this relationship between the inputs and the outputs. So if there's a discontinuity here, it will wash through into that derivative. For a second order system, we have this other situation where we have systems moving into one another, and so the second system does not see a discontinuous input, it sees a continuous input. So I had a discontinuous input in this system, but that system's output was continuous, which means that this system's derivative will be continuous. And so I can then use this to go and connect the logic backwards and say, how do I distinguish between this thing, which is a second order response, and this thing, which is a first order response? Here I'm seeing a discontinuous first derivative. First derivative because it's sharp. A sharp distinction between the pre-zero value and the post-zero value means that there's a discontinuity in the derivative. In fact, we know what the derivative looks like. It looks like the green line over there. And we can see that goes from 0, steps discontinuously up to that value, and then goes down again, right? In the second order case, I've also drawn the impulse response, which you will remember is the derivative of the step response. And here the impulse response starts at 0. Right? And again, so the step response has this smooth value at the time 0, and so we can see that that happens.